So first, a bunch of people have asked me about the slides and the videos, and I double-checked, and everything will be available online at some point, maybe not today or tomorrow, but in the next few days. We'll send out an email probably after AmCamp ends with a link to all the slides and the videos. So they will be available eventually. Second, this is my second of what will be maybe 3 or 4 reminders to start transferring data from your USB keys to your computer. So again, for those of you who missed the first announcement, the USB keys that you were given when you got here contain information that you need for the exercises. They're also kind of large, so you should, move them, and you eventually need to move them to your computer if you can. You can also run them from the USB key if you need to, but things will be pretty slow. Anyway, so please start that transfer process now if you haven't already. And on a related note, some small fraction of these USB keys were not created correctly. So before making this transfer, double check that the USB keys themselves are properly formatted. What you're looking for are 2 things. 1, that the USB key contains roughly 2 gigs or more of content. And 2, that you see 6 folders and a README in the USB. All right, a second announcement related to getting set up is that, so if you're remote, there are people who are watching this who are not here, you can get all the content of a USB key online at the following website. And now for everybody, both on-site or off-site, there is an additional set of small zip files that you have to download in addition to what's on your USB key. And assuming that and it'd be good if you could also start that download process now as well. So I'm going to show you really quickly where to go for that. So this is on AmCamp, let's see. This is AmCamp 5 exercises getting started. And basically, there's a section here that says additional resources, or additional required resources. There are different links for people on-site and people off-site. If you're on-site, you should be connected to the iHouse Wi-Fi, username AMP, password CAMP. And download and unzip this zip file. If you're remote, sorry? Oh, sorry, yeah. Better? Good, so go to this website, AmCamp 5 exercises getting started, and scroll down to the additional required download. And again, if you're local, if you're here, make sure you're on the iHouse Wi-Fi and download the zip file. If you're remote, just click the alternative zip file. All right, that's it. Great. You'll be hearing this again. I apologize. I just want to make sure that as many people as possible are set up before the exercises actually start. Okay, cool. So now, it is my absolute pleasure to introduce the next speaker. Happens to be me. Anyway, I was a postdoc in the AMP lab. I led the initial development of the MLlib project with many other people as part of the MLbase project. I'm currently a technical advisor at Databricks, also an assistant professor on leave at UCLA, and my interests are in large-scale machine learning, in particular scalability and ease of use issues related to machine learning. All right, so what I'll be talking about today is MLlib, which is, as you've heard so far, is Spark's machine learning library. And there'll be 3 parts of my talk. I'll first go over the history and an overview of MLlib. I'll then show some sample applications of MLlib, and finally talk about ongoing development and where we're going moving forward. Okay, so MLlib started as part of the MLbase project. So the MLbase project is an active project in the AMP lab, and the goal of this project is to simplify the development and deployment of scalable machine learning pipelines. So this project started about 2 years ago, and being in the AMP lab, we wanted to build large-scale distributed machine learning on top of Spark. But it turned out as we tried to do this, and in fact, what we really wanted to do was get to higher-level functionality, automation, and introducing higher-level APIs and frameworks to make machine learning easier. But to start, we needed a core set of machine learning functionality that we could build on top of. And it turned out that Spark was really chugging along, but it was sort of lacking this. So the first thing that we did as part of the MLbase project was actually develop this core set of machine learning functionality, which turned out to be which we released as the first version of MLlib. But then moving forward, we've started to move on to higher level components of our stack. So 2 higher level components, MLI, which is something we worked on last year, and pipelines, which is something that is being worked on in the lab right now. It's a current project that you'll hear more about tomorrow. These are APIs or frameworks to simplify machine learning development. So MLI is this API that prevents common abstractions to users, to developers, distributed tables, distributed matrices, and underlying optimization primitives that are more natural for a machine learning developer to reason about and therefore simplify the development of machine learning. The Pipelines project is a framework for putting together different pieces of a pipeline and try to make that the entire process easier to develop. And again, you'll hear more about that tomorrow. And finally, MLOps, which is the top layer of MLbase. The goal here is to create a declarative layer to automate the process of hyperparameter tuning of machine learning algorithms and pipelines. And the reason I'm talking about all these different pipelines is that MLlib is still very much related and tied to, integrated with these higher level components. And what I mean by that is that whereas MLlib is part of Apache Spark and it's a production quality code that it's used by a wide range of people, a lot of the ideas that are going into MLlib have their roots in MLI, pipelines, and MLOps. These are more experimental test beds, and we've already seen, and I'll mention throughout the talk examples of this, but we've already seen several of the ideas from these higher level experimental pieces of MLbase feed into MLlib once they become more mature and well tested. Okay, cool. So that's MLbase, but now moving on to MLlib. As I mentioned, it started as part of the MLbase team in the AMP lab. It started off as a fairly small project. We wanted enough core machine learning functionality that we could build on top of it and make progress on other parts of our project. We initially supported Scala and Java. We shipped it last September, but we started working on it 6 months earlier than that. But basically, as you've heard already, it's really one of the fastest growing projects in the Spark community. It's just blown up. 15 months later, we have 80 plus contributors from many different organizations. We've added Python support. We've added a huge number of additional functionality. And the most recent release is in Spark 1.1, which is in September. And as Michael was mentioning, there's going to be a new release in December. All right, and so what's in MLlib? This is just examples of some of the highlights of MLlib, and even this list is long. So I'm not going to go through the whole thing, but I would like to point out some high-level ideas. So we have algorithms for collaborative filtering for recommendation, algorithms for prediction, and by prediction I mean here classification, multi-class classification, and regression, clustering, k-means clustering in particular, optimization, and here I mean underlying optimization primitives that are used to develop a lot of the supervised algorithms that I just mentioned. And finally, there's a lot of additional utilities to help support the development of machine learning pipelines. Okay, and moreover, what are some of the benefits of MLlib? Well, at this point, you've heard some of them already, and one key benefit is that really being part of the Spark ecosystem affords a lot of benefits. So you have this integrated system where, sure, you can do machine learning. I love machine learning. I think it's really challenging. There's lots of cool problems. But of course, machine learning isn't the only thing you need to do when processing your data. And the fact that you're in Spark and you can process SQL queries or stream in new data or consider your data as a graph seamlessly and then use the output for machine learning is a really powerful thing to have. So this interplay between all these different pieces, along with just the functionality that Spark itself provides, is powerful for MLlib. Beyond that, and again, I think this was mentioned earlier, we've already started to see that we sort of get performance gains for free sometimes. And I'll show a few results, or I'll show a result of that form later on in this talk. But the idea is that as Spark itself gets faster, because we are built on top of Spark, for free, our code just sometimes runs faster, which is always a nice thing. All right, but beyond that, what we think is good about MLlib is one, that it's scalable, and I'll show a result about that later. We support various common languages that people like to use. We have broad coverage of various applications and algorithms, and some of which I mentioned before, and this list is rapidly growing. And yeah, we're rapidly improving in terms of speed, robustness, and the types of functionality that we're supporting. Okay, so that's an overview. Next, I'd like to talk about some example applications. It'll provide some use cases for how people commonly use machine learning, along with a very gentle, high-level overview of some of the core machine learning problems people try to work on. It'll also highlight, on a high level, some distributed machine learning challenges that we had to face when implementing these algorithms at scale in Spark. And finally, I'll present code examples related to these different problems. Okay, so we're first going to start with clustering. So, and in particular, k-means clustering, which is what we support in MLlib. And the idea of clustering is, imagine you have a bunch of data, and you sort of want to see if, it's unlabeled data, you don't have answers or, labels associated with them, but you want to kind of explore this data and see if there's some patterns that are emerging from it. And in particular, you want to see if they form meaningful clusters. So, one canonical example of clustering is, imagine you have a bunch of documents, so text-based documents. You come up with some way to represent each of these documents. So for instance, the simplest way to do that would be maybe to take all of your documents, represent them by the words that appear in the documents along with the counts of how many times each of those words appear. And basically now you have each of these documents as a vector with the number of words you're considering in their counts, and you want to see similarities and patterns that are emerging between these different documents. So for instance, you can imagine maybe documents that are about politics versus sports versus business are going to be clustered slightly separately. Or even, about different sports themselves would be clustered separately. But anyway, the idea of clustering is to try to explore these connections and clusters within your data. All right, so how can you do this? So the way k-means works is it's a pretty simple idea. You start with your data just as it is, and you in some way initialize your model by you say, okay, I want to find 3 clusters in my data. You pick 3 cluster centers. And you can do this randomly or slightly more intelligently or cleverly to get better results. But in some way, you pick these 3 cluster centers. Given these cluster centers, you then perform the second step, which is assigning each point to each of these cluster centers. These cluster centers are often called centroids as well, so I'll be using that word. All right, so you first pick centroids. You then assign your data points to each of these centroids. You then recompute the centroids. So now I have, I've colored all my data points in. I want to find new centroids that best summarize each of my clusters. So I have new cluster centers. I then go back with these, now I hold the cluster centers fixed again and reassign points. And you do this over and over again iteratively till hopefully you converge to something. So that's the idea of k-means. And the question is, how do we do this in a distributed setting? And it turns out that this is actually a fairly, k-means maps pretty nicely to the distributed setting. So recall, in Spark here, we're considering we have a lot of data, and we have our data stored horizontally, basically by data point, on a bunch of different machines. So we want to do this in a communication efficient way, computing this k-means. The two important things we have to think about, one is an algorithmic trick, which is that you want to be clever in terms of how you initialize your data points. So with k-means, one of the issues with it is that if you arbitrarily pick your cluster centers, or in general, it converges to a local optimum. And you don't know if that local optimum is going to be very good. It turns out that fairly recent work, especially given how long k-means has been around, but fairly recent work shows that you can pick data-dependent cluster centers to start with, and doing so shows that you can converge to an answer that's, epsilon good. I can't remember exactly what number, but it's a reasonable approximation to the global maximum clustering that you can get. So if you're smart, and there's a fast distributed way to also compute these cluster centers in a smart way. So one, you have to be smart about how you initialize. But then beyond that, you have to think again about communication. And as I was mentioning, it turns out that k-means maps really nicely to the distributed setting. So again, you have all your data distributed. You really don't want to move your data around across iterations, but it turns out you don't have to. The only information that you have to share across different worker machines is the current state of the clusters. And typically, you have many, many fewer clusters than you have data points. You might have 10 or 100 or so on. And the amount of state required to represent these clusters is pretty small. So basically, the idea is that on each iteration, you're broadcasting the current centroids, or the current cluster centers to each machine, do whatever computation you need to do, return back to the master, and repeat. But because your cluster centers, there are few of them, you're all right. OK, so how do you actually invoke k-means in practice in Spark? So here's a code snippet in Scala. What we're doing here in the first piece is basically just taking a text file, parsing it. We have space-delimited data, and basically we're converting that into an RDD of vectors of doubles. So this parsed data is a vector of doubles, an RDD of doubles. And notably, it's important to note that you cache this data. Again, this is an iterative algorithm, and a nice benefit of Spark is that you can store state across iterations, and you're going to continually on each iteration compare each of your data points to the current cluster centers. So you want to load that data from disk once, cache it, and then never have to do that again. So that's important. Once you've done that, you basically call k-means.train. You feed in this RDD storing your data. You tell the algorithm the number of clusters that you're looking for. So in this case, k equals 5. And you tell the algorithm the number of iterations. Here we're using 20. In practice, you might want to use a little bit more. And then finally, you run the algorithm. The algorithm returns your cluster centers. And you can evaluate the accuracy or the quality of your final clusters. And what we're doing here basically is this evaluation is seeing how well our cluster centers fit our current data. And basically what that means is comparing distances between each point and its assigned cluster. And the closer your points are to each of their cluster centers, the lower your error is going to be roughly. All right, so that's how you do it in Scala. Python, I'm not going to go through this code. It's pretty much the same, but the idea is that, again, you load your data, store it as an RDD, call kmeans.train, and again, you can evaluate your clustering error afterwards. Okay, cool. So that's how clustering works. Let's look at recommendation, which is another common thing people do in practice. So what are you trying to do in this task? The idea here, and I'm going to use a canonical example of trying to recommend movies for users. So the idea is here you have this table of users by movies, and some users have rated some movies, and you want to impute the missing, entries. So how can you go about doing this? Well, intuitively, one natural way to think about this. So imagine this first row. We'll call this guy Bob, and you want to compute, the missing you want to predict his rating on the Blue movie. Well, the first thing you might want to do is say, okay, who does Bob look like? Who are other users that Bob might look like? And maybe I can transfer knowledge based on finding similar users. So you might look through this, this row of people and notice at the bottom row, this guy we'll call Kenny. Kenny and Bob agree on the first two movies. So you can transfer Kenny's label for the Blue movie to Bob, right? And you kind of want to do this similarly similarly, you want to use existing ratings to impute missing ratings. This is called a collaborative filtering problem. But there's some clear challenges that exist for collaborative filtering. So one is that how do you define similarity? So in this particular example, we said that Bob and Kenny are similar, and therefore you can just transfer ratings between the two. But similarity isn't usually so well defined. In the context of movies, Bob and Kenny both might like action movies, but maybe only Kenny likes romance movies. That's a toy example. But basically, defining similarity isn't so straightforward in practice. People are more complicated than that. Second, these problems tend to be really large. So, you have millions of, Netflix has millions of users and hundreds of thousands, if not more, of items that they're hosting to people. This problem isn't just for Netflix. For, Amazon has items and users as well, and many other examples. These problems get pretty big, pretty large. So there's lots of entries that you're trying to impute, and you're also dealing with very sparse data. So basically, you have this huge matrix. You've only seen a very small subset of the entries. What makes you think that you can actually impute the missing entries? You sort of need to add more structure to the problem. So what people often do in practice is they assume that ratings are determined by users in movies or users in items, their preferences are determined by a small number of latent factors. And this is also, people call this making a low rank assumption. And what this looks like pictorially is basically I have this ratings matrix, and instead of saying that all the entries are just independent, I'm saying I make this assumption by saying that the structure of this matrix can roughly be defined as the product of user factors, where each row of this user factor corresponds to a particular user. So this first row corresponds to Bob's latent factors, times movie factors. And so this short fat matrix is basically each column of it is corresponding to a particular movie's factors. And doing so makes things a lot easier for you. So now imagine you're in this setting where you're trying to do collaborative filtering. You have 25 million users, 100,000 movies. So this matrix is really big. You have 2.5 trillion entries, of which you've probably seen 1% at most of them, probably many less than that. There's no way to learn all the parameters from that small subset of data. But when you've constrained this problem by having 10 factors for user and movie, you have many fewer parameters you're trying to learn. It also means that your model it's still really big, but it's smaller. It's hopeful to maybe try to learn from it. So that's kind of the idea of what you're doing in this low rank-based collaborative filtering approach. And what are ways to solve this? Well, there's various ways to solve this, but one very common way, and what we do in MLlib, is use the alternating least squares algorithm. In ALS, it's similar. It has a lot of similarities to k-means, with the idea that you're alternating between two steps. You hold one thing fixed while solving for the other one, and then you alternate back and forth until you converge to something. So here, you're alternating between training the user factors and the movie factors. And the whole time, of course, the movie factors, the ratings that you've seen, they stay fixed, because that's your labeled data. So basically, in this picture here, I'm fixing the user ratings, learning the movies, and then vice versa, and back and forth until I've converged. Okay, so there are good and bad things about this algorithm. The good thing about this algorithm is that it really is embarrassingly parallel, so it's great in one sense for a distributed setting. And what I mean by that is that, while I'm learning, let's say, the user factors, I can solve for an update for each of the user factors in closed form, completely in parallel. So, basically for each of these user factors, I'm solving some linear regression, and it's embarrassingly parallel. So that's great. The problem is that these models are huge, and there's a lot of inherent communication that's required for ALS or any other algorithm that's trying to solve for these sorts of models. And so there's a lot of communication that's involved in performing each of these steps, even when you're doing things in parallel. And of course, in a distributed setting, you really have to be careful about communication. So I'm not going to go into any more detail about how we actually do it, other than saying that we do it very carefully, and I'll have one slide about performance later that sort of suggests that what we're doing is reasonable because we scale. In addition to being fast, we scale quite well. Okay, and again, this problem was motivated by the Netflix, at least in academics, there was this Netflix challenge in 2006 or 2007. It led to a lot of really cool academic work. But of course, this problem, lots of problems can be cast as collaborative filtering recommendation system problems. For instance, Pandora or Last.fm, they want to predict music, or for link prediction, or for items and users and so on. So it's a pretty common problem, and we scale pretty well. All right, and so how does this look in terms of code? So here's an example in Scala, and again, the first part is basically taking your data and parsing it, and basically what you want to do is take your data and store it as an RDD of what we're calling ratings here. This is just an object that stores a tuple of user ID, movie ID, and the rating. And intuitively, again, what we're doing here is ratings is an RDD that's sort of storing a sparse matrix. We have this huge matrix with lots of dimensions in both in both users and items, but it's very sparse, so you clearly need a sparse representation here, and that's what this ratings RDD is getting at. All right, so once you have this ratings RDD, you call als.train, and you feed to it this ratings matrix. In addition, this low rank parameter, the rank here again is the number of user and movie factors or item factors that you're assuming in your model, number of iterations, as well as a regularizer. I didn't talk about that here, but that, roughly speaking, is trying to prevent you from overfitting. All right, and once you've trained this model, the model returns these user and movie factors that can be used for subsequent prediction. So what we're doing here is kind of a toy thing you wouldn't actually do, but basically we're taking the set of training data, so all the user movie pairs for which we actually have ratings, and we want to see what the predicted answer is. So we're doing, so user products basically is an RDD storing tuples of user ID product IDs. We feed each of these tuples to the model for prediction, and out comes an answer. Okay? And you'll get more of an opportunity to play around with ALS today. This is what you'll be doing in your exercise after lunch. So what you'll be doing here is, so you're first going to be loading a data set. It's this movie lens data set. It's not so big, but it's illustrative of what's going on, and it's very commonly used in academics to benchmark various collaborative filtering algorithms. But you're then going to augment this data set with your particular examples. So, we're going to ask you to rate some movies in this set of movies that MovieLens contains. You're going to take this augmented data set, split it into a testing and a training data set, and using the training data set, you're going to fit a model, either using Python or Scala. You're then going to try to improve this model via hyperparameter tuning. And this is related to this idea that I talked about earlier with MLbase, the top layer, MLopt. The idea is that models are pretty sensitive to various parameters. Here, the parameters could be the rank or the number of factors that you're allowing each of your user movies to be represented by, as well as this regularization parameter, which is preventing overfitting. And basically, you're going to try a variety of parameters to see which model works best, or which set of hyperparameters, which instantiation of hyperparameters works the best. You're then going to use that trained model to predict movies for you. These movies would be maybe useful for you back in 2001 or 2002, given the age of this data set, but hopefully it'll be something interesting. Okay, cool. So those are some example applications. Hopefully that gives you some idea of how, the high-level thought process behind designing algorithms in MLlib, as well as how you invoke things in MLlib in practice. I'd like to spend, the last few minutes talking about ongoing development, as well as provide some performance results for MLlib. Okay, so first, here are performance results. This is with, I think, Spark 1.1. It's comparing, it's using ALS, this collaborative filtering algorithm that I just spoke about, and it's using an Amazon Reviews data set on 16 nodes. And it's using this Amazon Reviews data set along with synthetic variants of it where we make the data set bigger and bigger and bigger by replicating some users in that data set. So statistically, it makes the problem easier, but computationally, it's a reasonable thing to do to benchmark performance of various algorithms as you have larger data sets. And what we're comparing here, so on the x-axis, you're seeing this Amazon Reviews data set or bigger and bigger variants of this Amazon Reviews data set. On the y-axis, you're seeing how long it takes to run. I think this is 5 or 10 iterations. You'd probably run it longer in practice, but again, this is just comparing two things. And basically what you're seeing is that MLlib's a lot faster than Mahout. 10 to 100 times faster, which is cool. But I would say that beyond just this, the speed increase is maybe sort of expected given that these are iterative algorithms and we're caching between iteration for Spark and we're not in Mahout. So maybe that's not so surprising. But the fact that we scale better as well is, I think, illustration that we're implementing our algorithm in a way that's reasonable to handle the communication burden that's inherent in this algorithm. So similar experiments were performed on using the same sort of setup, but on a bigger cluster with 50 nodes and on a bigger data set of, a bigger synthetic Amazon Reviews data set with 660 million users and 2.4 million items with 3.5 billion ratings. And basically, on this pretty large data set, we were able to run MLlib in 40 minutes. So, we can scale pretty well to large problems with, as we use bigger and bigger machines or bigger clusters, which is pretty cool. Okay. So also, beyond just, Spark or MLlib being faster than some competitors, we've also noticed that Spark continually gets faster compared to itself. So what we're seeing here is this is speed up between Spark 1.0, which was released, I think, in July, versus Spark 1.1, which was released or maybe June. Spark basically in a 3-month window between 1.0 and 1.1. And these are for 3 or 5 commonly used algorithms in MLlib. And basically what we're seeing is that we see steady performance gains across these different algorithms and on average a 3x speed up. And we're seeing these, I think, for 2 main reasons. So one, as I said before, because MLlib is part of Spark, sits on top of Spark Core, as Spark Core gets faster, MLlib gets faster as well. And an example here is, so a lot of these algorithms in MLlib require broadcasting parameters on each iteration. So k-means, you have to broadcast your centroids. For linear models, again, you have to, if you're doing gradient descent-like algorithms, you have to broadcast the current parameter vector on each iteration. And Spark Core introduced torrent broadcast between 1.1 and 1.0, which led to a big increase a big performance boost for all these algorithms that rely heavily on broadcasts. That being said, there was also some algorithmic improvements within MLlib itself that increased performance, and notably, in particular, decision trees. They were introduced in 1.0, but they were heavily tuned and optimized between 1.0 and 1.1 to make them a fair bit faster. But anyway, the point is that we're seeing things get faster, which is kind of neat, and part of it is coming from Spark itself. Okay, so I'm almost done. The next thing I'd like to note is that we are, one new thing that's happening in Spark that you're going to see in version 1.2 is support or framework for ML pipelines. So what I mean by that is, let's consider a typical machine learning workflow. You start with some training data. You take that data, you extract features. So for example, in the text case, your features could be, the bag of words, counts of how many words appear. You then train a model. You then, you have this model, you want to test it with some test data, but it's not really quite that simple. There's a lot of other things you have to do. You have to do feature extraction on your test data. You might have additional data that you also want to merge in either directly or via another model. You also have to repeat this process over and over again as you want to tune various hyperparameters of the different stages of this pipeline. So the point is, this is a pretty complicated thing to do, and we want MLlib to provide functionality to easily compose different pieces together and develop frameworks in a natural way. So what's being released in version 1.2, and this is an alpha release, and what that means basically is that it's a release that, it's open, people can use it, but we're not promising that the APIs will remain fixed between 1.2 and afterwards. But so this alpha release, the main goal is to make construction of these workflows easier, provide standard interfaces between different components of the model, as well as for model tuning. And basically, be able to inspect different components of this pipeline so that you can fail early. You don't want to run for 10 hours before noticing that there's something wrong with the 4th stage of your pipeline. So trying to catch things early when possible. And I should note that this is a great example of the interplay between MLlib and the higher level components of MLbase, as this ML pipelines work is very much inspired by the pipelines project within MLbase. And again, Evan Sparks is going to be talking about this tomorrow. So, and I actually would defer questions about this pipeline stuff to him. I think he's here today. But that's a really cool thing. Also, this is a collaboration with Databricks. There's two folks there who are working closely with Evan and some other guys in the AMP lab to take these research ideas and make them, production ready. And finally, this also ties in with what we want to do for the highest level component of MLbase, where again, the idea is that we want to auto-tune hyperparameters of pipelines. So having this infrastructure in place for MLlib allows us to take our researchy ideas that we're developing and eventually move them into MLlib using this infrastructure. And the second API piece or infrastructure piece that's being added into MLlib is related to datasets. So of course, when you're working with an ML pipeline, you start with a dataset. This dataset can be sort of messy. It could have missing data, different types for different fields. And we want an object that can naturally support this sort of data. Keeping metadata about different features, allowing you to quickly select subsets of features or join different features together. And the cool thing is that, in Spark, I think in version 1.2, this ML data set is going to be supported by a schema RDD, which is what Michael was speaking about when he talked about Spark SQL. So this illustrates integration between MLlib and Spark SQL and, advantages of having these different components together in the same framework. This also illustrates another nice example of, MLbase interacting with MLlib, as the MLI API was exactly targeting these sorts of ideas. We wanted to come up with distributed tables and distributed matrices and basically support the sort of common use cases that machine learning people deal with when when developing machine learning pipelines. So these things are all connected and coming together in a really neat way. All right, so that's the end of my talk. Hopefully I've given you a reasonable overview of MLlib, where it came from, what it consists of, where we're going. But I'm sort of just scratching the surface, and I'd encourage you to check out, there's a lot of cool resources online about MLlib. So first and foremost, the programming guide provides all the nitty-gritty details about what's there and how to use the different pieces of MLlib. Databricks also has some really nice training information, so you can check out their website. As well as if you have questions about using MLlib or contributing to MLlib, the Spark user and dev list, the community is very vibrant. You can check out, join the mailing list, post, ask questions, ask what needs to be, what would be interesting things to contribute to if that's what you're looking to do. And finally, I'd also like to note that I'm working on developing a MOOC, a massive open online course on edX that talks about scalable, or that presents basically the core ideas about scalable machine learning and basically the nuts and bolts and nitty gritty behind how we're developing all these algorithms within MLlib. So this course will be in April, but you can register for it online right now if you're interested. It's free to everybody. And again, related to that, in January, I'm co-organizing a mini course with Anthony Joseph and Paco Nathan. This is hosted by BIDS, which is the Berkeley Institute of Data Science, for those of you who don't know. And it'll be based on many of the ideas that'll be in my MOOC and another MOOC about Spark more generally. So I don't have a website about that yet, but if you're interested, let me know, and I can let you know when registration for that is up. Okay, that's it. Thanks for listening. And let's see. I think we're a little bit behind time, so maybe I'll take one question, but maybe Encore should get up. Where's Encore? Yeah, do you want to get up and get set up while I take questions? Okay. Questions? How is Spark R? So the first thing I'd say is that there's going to be a talk about Spark R tomorrow. So the right people to talk, Shivram and Zhong Heng, who were talking about Spark R, I think are more equipped to type. But what specifically are you asking about? Sure. So R has great machine learning packages available, but none of them are distributed, right? So if you want to perform R-based things locally on subsets of your data, you can do that. But yeah, I think that you should be talking to Shivram about. I mean, there are fundamental differences between Spark R and MLlib, and there are connections. But I think I'll let Shivram talk to you about that tomorrow. So how about you two? So first him, then you. Sorry?
Spark can integrate with H2O.
Sure.
So H2O comes with its own suite of deep learning,
Sure.
random forest, all of that stuff.
Yep.
So how are you guys going to integrate it together with that?
Yeah, so especially with the random forest, I would say that, so they have an implementation. There was another company whose name I'm blanking on right now who had their own implementation of random forests. We have our own implementation of decision trees. And the goal is to, the best one, whoever it might be, if people are willing to share, should go into MLlib, right? If this is a thriving community, we need good implementations that everybody can use. So, again, I'm blanking on the name of the other company that was working with us on the decision trees, but a lot of the ideas that are in decision tree in the current decision tree code, and a lot of the improvements that we made between 1.0 and 1.1 came from sort of inspecting these two different code bases and picking the best from both of them. So, that sort of answers basically when people are willing to contribute to MLlib or basically improve the current state of the art, whatever is there, we're very welcome to that. All right, so I'll answer one more question, and then I'm happy to talk later.
So you mentioned the need to catch RDBs for iterative algorithms. What happens if the cluster does not have enough RAM to cache everything? Does it fail hard?
No.
Does the performance degrade?
It degrades. I mean, that's exactly what Michael was mentioning. Spark does not break by any means when you can't cache everything. So, okay, great. I'll answer more questions later, but for now, I'd like to introduce Encore.